Well, hello everyone and welcome to the first of our part 5 videos on the chapter 8 material, continuing our look at addition to carbon-carbon double bonds. In this particular set of videos, we're going to take a look at the dihydroxylation reactions and take a little bit of look at the mechanism of how they occur and pay some attention to the stereochemistry of those reactions. So let's take a look at the overview of one of our first reactions that we want to take a look at here, which is the dihydroxylation. And we've got cyclohexene, a carbon-carbon double bond containing molecule. We've got a couple of reagents that we'll look at in some more detail in a minute. The two reagents are metachloroperbenzoic acid, and we'll draw that out in some detail in the next screen and look at its structure, and then we'll look next at the mechanism of it. And again, that's for reagents treated first, and then second is that product of that reaction is treated with acidic water to yield a dihydroxylation reaction. So again, the 1 and 2 above and below the arrow, as we've seen in previous videos. And so the result of this particular reaction are dihydroxylation, where what we observe here is that the dihydroxylation goes in the antidihydroxylation. That is, the two OH groups are on opposite faces of that ring with respect to each other. They're trans in the end, so they come in on opposite faces of that ring. And the other thing that we also observe about the products that we form here in this instance, we've got a pair of enantiomers. And again, I've just drawn them in a particular way. We'll look at the mechanism in a little bit of detail about how we get to that pair of enantiomers. But first, let's look at this reagent, metachloroperbenzoic acid. So MCPBA, here's the chemical structure of this molecule. It's an aromatic ring with a chlorine there at the so-called meta position. And again, we haven't talked about that at all this term. We haven't seen much of the organic nomenclature. So just at that position, right adjacent to the other substituent that's already on the ring. We've got an oxygen and another oxygen, make a hydrogen and a hydrogen attached there. So metachloroperbenzoic acid. Metachloroperbenzoic acid. There's the acronym, the derivation of the acronym. There's the chemical structure of the molecule itself. Well, we'll look in a little bit of detail about how this particular molecule reacts, but I'll just point out that what we have here is we've got a reactive peroxide bond. A reactive peroxide bond, and we'll look at how this participates in this mechanism and leads to a dihydroxylation product. So let's look at this in some detail here. There's our alkene, or cyclohexene is that particular molecule, and what I'll line up here is the oxygen of that perbenzoic acid. Where R is the rest of that aromatic ring that we saw just a minute ago. I'll draw in some lone pairs of electrons here just so we can kind of keep track of it. And what we have evidence for this as being the reaction, or the mechanism of this particular reaction, is that what we think is, again, that bond of the carbon-carbon double bond acting as a nucleophile to push off as a leaving group here, that oxygen. A pair of electrons comes in and forms a new carbonyl group. Those two electrons go onto the oxygen, and two of these electrons come and grab that proton, and those two electrons come in to attack one of those bonds there. So a lot of arrows to kind of explain this whole mechanism here. I'll just move this up and over and out of the road a little bit here. Well, we think the intermediate, and again, I'll just, or that, more correctly, the transition state on this, the transition state looks something like this, where we now have that carbon double bond is being broken. And I'll draw these in blue just so I can keep track of them. These so-called kind of partial bonds. That oxygen is being, a new bond is being formed between the two carbon atoms and one of those oxygen atoms. And at the same time, the double bond is disappearing. Meanwhile, our reagent is over here. There's that R group. That hydrogen is kind of trapped in the middle there. And we've got partial bonds all kind of being formed all the way around here, where that hydrogen is coming off of the oxygen and going on to the other oxygen of the carbonyl group that started life as the carbonyl group here. I'll move this bracket in here just to make some comments on this here. So we think this is concerted. That is a single step. And that the product of this particular reaction ultimately leads to a new covalent bond between the oxygen and the two carbons that were participating in that carbon-carbon bond. So we make a structure that looks like this. The other side product is metachlorobenzoic acid, so the product of this behind. But the main product the major product that we're concerned with is the epoxide. An epoxide, three-membered ring with an oxygen containing bonds to a couple of carbon atoms. And so that's the first product of this reaction. It's not an intermediate, it's a true product. And in fact, you can isolate the epoxides if you choose to do so. But typically what we do in these dihydroxylation reactions is we take that epoxide on to the next step without isolating it. So then let's take a look at the next steps in that mechanism. There's our epoxide that we just had a minute ago here, and I'll put it in the very center. Now the other reagent that we have in this particular reaction is H plus and water, or H3O plus. Of course, we know that's the way it exists, but we just like the kind of convenient shorthand of writing it as H plus and H2O. Now, with excess protons around, there's a nice source of electrons there to attack that proton, and that's the oxygens of that, the electrons on that oxygen of the epoxide. And again, we could draw this in equilibrium. So we get this protonated epoxide intermediate. And so now if we're looking at that, we'd recognize that that's likely going to make a pretty respectable leaving group. So that'll allow us to participate in some chemistry on the next page here. So let's do this. I'll shrink that down a little bit because we've seen it already and just kind of hide it out of the road. And what I want to show is the two different fates of this particular intermediate on our pathway. Now, drawing that molecule of water, I've drawn it backwards there just specifically because we're going to take a look at sort of the fates of this particular molecule. In a minute, we've imagined two possible pathways for that water molecule to act as a nucleophile. And I know we say it's not a great nucleophile, but look, it's opening a three-membered, highly strained ring into an intermediate where there's already a positive charge on that oxygen. So overall, it's a pretty decent reaction based on all the things we've talked about here. So we can imagine one pathway here that I'll draw in red, where we can imagine a lone pair of electrons on that water coming in to attack the back side of that carbon atom and ring opening that epoxide on a pathway that looks like this. So that's going to attack the back side of that leaving group, just like effectively a nucleophilic attack like we've seen before, and that's going to go from the underside or the least hindered side of this molecule. We'll make an O. And that'll take off that proton, and we're left with a product that looks like that. Now, of course, if we're looking at the pathway, we recognize there's a second possibility here, and so that we can bring another lone pair of electrons and attack the other carbon. I'll do it on this blue pathway here. Those two electrons going up into the oxygen to satisfy the positive charge on it. I can make a ring here. And now that oxygen that started life as the epoxide ring opens in the other direction, and now we have pointing down that molecule of water. But now in a step that we're really quite familiar with, it comes in and takes off the proton. Giving us that molecule, which if I turn it around here, if I just rotate it on the plane of the page, you recognize that that's of course the enantiomer of the first molecule that we drew. And that is how we get to the two enantiomers, is we form the epoxide and we get attack on either side of that epoxide by the water that we're using as a solvent. So next, let's take a look at the stereochemical outcome of this particular reaction when we're looking at acyclic substrates. So stereochemistry here. And what I want to start is with an alkene. With the Z configuration around that double bond. Z configuration. So now let's look at what happens to this particular molecule as we form the epoxide. We form an epoxide that looks like that. So again, coming in, forming that three-membered ring, the two methyls are on the same side of that three-membered ring and the two hydrogens are on the same side of that three-membered ring. And so now let's take a look at what happens to this particular molecule. I'll put in a molecule of water at the bottom here. I'll put an H plus over here. And let's look at what happens if we attack that with the attack that H plus and attack this carbon atom. Attack this carbon atom with the water molecule of water to ring open in that direction. What we'd observe over here is that's the red proton. We get something that looks like that, where that incoming water is coming in from the opposite side of the molecule, from where underneath where the epoxide and its ring opened. And so of course, if we're looking at this particular conformation, we recognize there's another conformation that we can make here. And so just for us to be able to keep an eye on the stereochemical relationship of these molecules, Like that, we'll rotate it so those methyl groups are kind of pointing up and down. And again, if you're having trouble following this, the model kits will be a real big asset for this as well. And what we want to compare is what happens if we attack the other side of this bond here. What happens if we attack the other side of this bond here? So again, with a blue proton coming in there, those attacking, and this opening up this way. We'll go down this blue pathway here, and the product that we get where this is the blue proton, so that is swung open. The blue line from the water molecules come in and attack the other side and is now pointing down. And so then again, if I rotate this just so that the methyl groups are kind of pointing in a direction that we're a bit more accustomed to, we get something that looks like that. And if you look at the stereochemical relationship between these two molecules, what you'll recognize is that they're enantiomers. So in the Z stereochemistry, if we start with a Z, we wind up in this case with two molecules that are enantiomers with respect to each other, and so that's the stereochemical outcome there. Next, we'll take a look at the stereochemical outcome of the E alkenes. So again, we'll take a look, just kind of draw these out. So the E alkene were the substituents on either side of the bond here. The substituents are on either side of that double bond. And what happens if we form the epoxide here? So again, we can form the epoxide, and then we want to imagine what's going to happen if we ring open, if we ring open that epoxide. We ring open that epoxide from the opposite sides here. So in a similar way that we did with the Z alkene, we can imagine a proton here. We'll put a red one in. We'll have this pair of electrons on the water, a pair of electrons from a water molecule attack that. The electrons attack there and go up onto the oxygen. Make a product that looks like this. Again, I'll circle that in red. So that's the red proton. That's the direction that epoxide is ring opened. Epoxide is ring opened here. We get here a proton here. Like that. And again, I'll just redraw this in a way that we're a bit more familiar with. Just to show you that in the end, those oxygens wind up on the opposite faces of the molecule if we draw that configuration that way. We draw that conformation that way, but all derived from this particular mechanism. Now again, let's look here quickly at the other sense of ring opening there. Again, attack on the other carbon, we can draw the blue pathway in here. And now, of course, the ring opens this way onto the oxygen, so we get something that looks like this. That's in blue now. And then I can draw this here. That looks something like, now again, putting those methyl groups like that. So again, those OHs ultimately in that conformation wind up on opposite sides of the molecule. Now, what we want to look at is what's the stereochemical relationship between these two molecules. So let me do that on a clean sheet here to be able to sort of picture what's happening with those two outcomes. Again, this is the blue, this is the red. And let me draw another conformation of this particular molecule here. And again, I'll show this as an eclipsing conformation. And if I do this, if I crank this down, and I'll do the same here. If I do the same there, what I recognize if I draw this particular conformation for both of those products that started out, and again, here's the blue proton here. There's the red pathway there. The two, oh, sorry, that should be in red, of course. There's the red pathway there. Those two pathways, nearly identical pathways, they gave us these two molecules. And if I look at these molecules, what I observe is they both have an internal plane of symmetry. I walk down those green lines, I look to the left, I look to the right, I see the same thing on both sides. So even though they've got two stereogenic centers, these are achiral mesomolecules. And in fact, I can draw my ridiculously equivalent symbol between those two molecules because they're perfectly identical with all respects to each other. They're superimposable mirror images of each other. There's an internal plane of symmetry. Those are achiral molecules. And that's the result of starting ultimately from the E alkene. So with that, we'll stop the video on the anti-dihydroxylation using MCPBA, and we'll finish this up by looking at syn hydroxylation.